Hello, my name is Azucena Lopez, and I'm part of the team also with Aziz, Bandan, and MD Rahman. We are doing this project of the course Machine Learning, and this project is about predicting the ozone concentrations near industrial areas of Houston, Texas, using linear regression method. The objective of this project is um, Houston, Texas is a city with a high concentration of industrial areas, which are known to be significant sources of air pollution. So, one of the major pollutants emitted by industrial areas is ozone concentration and is associated with health issues like respiratory problems. So this is one reason about to do this project, predicting also concentrations near these industrial areas of Houston, Texas, is essential to mitigate the health risk and reduce the environmental impact of air pollution. We are using the linear regression method to predict daily maximum 8-hour moving average ozone concentrations near these industrial areas of Houston, Texas. These industrial areas in Houston, there are five areas, which are the Port of Houston, the Energy Corridor, Bayport Industrial Area, East End, and Greens Point. These five industrial areas include different sites, um, and we will show you in the project. So for this project, we have these metadata variables. We selected five parameters that have an effect on ozone concentration prediction. The dates that we have selected for this collection of data are from January 1, 22 to February 23, 23. These criteria are ozone concentration, temperature, humidity, wind speed, solar radiation, precipitation. In this table, we can see the units and the source of information. It's important to mention that the ozone concentration is the dependent variable that we are using on this linear regression model, and the other five parameters that we are considering are the temperature, humidity, wind speed, solar radiation, precipitation are the independent variables that we are including in this regression model.
Go ahead now. So this is MD Mahabubur Rahman. So in our project now, I will explain the model. So in order to perform our regression model, first we actually make a Jupyter notebook. We need to import the data or load the libraries. So here after that we need to change the working directory from our in our computer. So if we run this model, here is also some comments. Set working directory, you will see load the data files as pandas data frame. Here is the Excel file where what we have run right now. So there are some no variables. We can't, as we can't give the model this kind of value. That's why we need some measurable value. So we change those things with the mean value of the each column, and in addition we don't need the index. That's why we replace this index with the date here. After that, yes, we have total 8 sets, so we will go side by side with the variables. So we select the relevant data from the one side, and here is the summary like count, mean, standard, minimum, and maximum value with the with like 25, 50%, 75% percentile. Then we can make the plot correlation matrix here. The matrix you will see it will come with the ozone, and after that we can get the heat mask by giving the heat heat mask. So yes, we don't need the upper value. We can do with the heat map.
Here, as you see on the heat map, there is like we can see the relations between all the variables. So here with the ozone, there is a radiation. So radiation and ozone have a strong relation. Just like that, the temperature and the radiation also has the strong relation. But after the radiation, there is one more variable is temperature, which is strongly related with the ozone. We can see that. And the less related variable is humidity here. That is with the ozone, humidity is less related to ozone. So as you we can find out the relations between the models, between the variables. So after getting all this insight, we will start with the regression model one. So we have prepared the three regression models by using the different variables, by using different variables each model. So there we have three models for only one site. We have this there is eight site. So we have all sites have three models. So let's start with the regression model one. So the model one is developed for the temperature and radiation. So here the independent variable will be the temperature and radiation, and the dependent variable will be the ozone. So here our X is temperature and radiation and the Y is ozone. So now we have for the model we have to split the data into training and testing. So training and testing for that we're gonna use the test size as 20%. So our 80% data will go in training the model. So here we can add the constant, then we will go to feed the model and get the summary of the model. So here I feed the model with training data, and I get this I got the summary of the data, of the training data. So here on the training data you can see there is a number of observation is 335 and the number of residual is 332. And there is also coefficient. You if you find coefficient, there is 0.08, that for x1 that is temperature, and the 41.88 that is radiation. And the standard errors is very low for temperature, and the error is a little bit high for like radiation. So we can get the overview from this result. Then we will go with like we will keep the copy and define the error. What are the errors in this? And like we will do the prediction for the test data. So this is the main part here after training the model. So we'll get the add the constants and predict the model for test data, and we'll find the error test. That is the error of test data. So that is y test minus y predicted. Now we will evaluate the model on test set. So now we can evaluate the model by predicting the mean square error, by getting the mean square error. So by getting the mean square error, that is 150.52, we have evaluated the model here. Now we have to plot the observed versus predicted plot. So this is the part where we have developed a plot a graph that is actual ozone versus predicted ozone. So these are the values for actual versus predicted. And now we have to test our model for homoscedasticity. This is the code for that. We can get the value of our BP, that is variable for the homoscedasticity. And now we have to test the normality of the error distribution. So by doing this, we will get the we can see here that we got fairly minimum, fairly distributed error. And at last we can do the auto correlation testing, that is the SM state, which is the auto correlation test, and we can get this coefficients of the autocorrelation testing. So this is the model one, and these are the results for these models. Now we have developed all three models by using four parameters, that is radiation, humidity, wind speed, and the precipitation. So my colleague will discuss, my team member will discuss about it, Aziz. So over to you, Aziz, now.
Yeah. So after doing the regression model one, they will move forward to do the regression model two. So what we've been able to do here is that we decided to replace the independent variables. So in this place, our independent variables are the precipitation and the radiation, while the dependent variable is ozone. So after that, we move further to splitting the data. So split the data into the trained data and then the test data. So we made it in the ratio of 80 to 20. So the train data is 80, while it's 80% of the total data, while the test data is 20% of the total data. So moving forward from that, we now decided to fit the model. So after fitting the model, these are the summary that we got. So we can see that so we use the least squares method to carry out. So the number of observations is 335, while the number of residual is 322. So our independent variables are two. So coming down here, this shows us the coefficient for the independent variables. So the first one, the coefficient is 0.3940, while for the second one is for the 7.196. The standard error is 1.398, while for the other one is 4.9975. So here are also some other tests that were done, like the W Watson test, the Jackie Berra test. So moving forward, from there, we decided to do the test data. So what we did here is similar to what we've done for the train data. We are simply using a less data. So meaning that we've trained the data. Now we want the data to actually carry out the tests to be able to evaluate our model. So moving forward, then we decided to evaluate our model, the test model, and then this is the mean square error that we got, which is 149.8. So then we now decided to move forward by trying to compare our the ozone concentrations. So we now decided to plot a table, a graph of the actual ozone and the predicted ozone. Here's what we found out from the graph. Then I decided to move forward to test for homoscedasticity. This is just an assumption of variance of errors in the model. So we decided to go a step further by doing a test of normality. So test of normality is just we want to know if our data is normally distributed, because this will determine if the model is actually appropriate for the test for the set of data that we have. So what we have here is the graph, and because they all lie along the slope, so it shows that the data in which we're using for the model is appropriate. So then we decided to go further to do an auto correlation test. So this is just to determine the relationship between variables of the test. So and also it will also tell us if we have bias. If this is wrong, then it means that whatever we get as a prediction are going to be biased. So moving forward, we decided to run a third model. So over here, we did the same thing we did in the second model, but just the difference there is that we changed the variables. Over here, we use the wind speed and we use the humidity. Then we decided to split the data as we've done. Then we also move further to fit the models, and here are the set of data that we got. And then we also move further to do for the test data. Then we decided to evaluate the data as we've done before. So here's the actual and predicted plot, and there's the test for normality that we did.
Okay.